Thank you. It is my pleasure to introduce Orna Kupferman. So Orna is a professor at the School of Computer Science and Engineering in Jerusalem, in Israel. Her research areas cover the theoretical foundations of the formal verification and synthesis of computer systems, with a focus on automata theory and game theory and their applications. And today she's going to talk about playing games on automata, and we are very excited to hear about this. So please say welcome to Orna.
Okay. I said nothing important, I just repeated the title. So if you are here, you are probably familiar with automata, so just to make sure you are awake, this is an automaton on finite words. Its alphabet is 0 and 1. What's the language? Finite words. When it sees a 0, it stays in Q0, or moves to Q0. When it sees a 1, it moves to Q1. Q1 is accepting, so it accepts exactly all the words W that ends with 1. And just for the sake of notations, this is how we are going to denote automata. They have an alphabet sigma, set of states Q, initial state Q0, transition function delta. And delta here is deterministic. Every state and letter goes to a single successor state. And the automaton runs on the word, and the run is accepting if it ends in a state in alpha. Alpha is the set of accepting states. So I assume you are all familiar with this. And you probably also know that an automaton can also be non-deterministic. And when it is non-deterministic, then each state and letter has several possible successors, and this is an automaton for the same language. And I still show it because I wanted to get used to the idea that when we have non-determinism, we like to think of it as if the automaton makes a guess. It makes a guess whenever the automaton is in Q0 and it reads a 1. This is when it has non-determinism. The 1 can stay in Q0 and it moves to Q, may also move to Q1. When will the automaton move to Q1? When it guesses that this is the last letter of the word. Yeah, so the automaton has some, I don't know, intuition, guess, or something, knowledge about the future, perhaps. And this is what directs it when it makes a decision not to loop here, but to jump to Q1. So the same language. And in this language, we had 2 states in a deterministic automaton, 2 states also in a non-deterministic automaton. But in general, non-deterministic automata may be smaller. If we generalize this example to all words that end in 1 in the letter end to the end, so a non-deterministic automaton can do it very easily. It still guesses, but now it guesses that, okay, now I'm reading the letter that is in position n to the end. And if I want a deterministic automaton for this language, it will be exponential. I have to remember vectors of length n. So non-determinism enables us to define more succinct automata. But for finite words, all this is quite easy. We know the subset construction, and nothing too surprising. Very nice. It's nice that they developed non-determinism, but from a combinatorial point of view, there is nothing too challenging. Non-determinism may be removed with an exponential cost. Now let's move to automata on infinite words. And these automata were introduced in the 60s by, I will call him Buki. It's Buki, but I will say Buki. And in a Buki automaton, it looks exactly the same. A run is a run, but now a run is infinite, so we cannot talk about the last state. But we know that there will be at least 1 state that is going to be visited infinitely often because the run is infinite, and the run is accepting if it visits alpha infinitely often. So for this automaton, it is going to accept all the words W that has infinitely many 1s, because whenever there is 1, it jumps to the accepting state and gains a visit in alpha. But automata on infinite words are more complicated. And let's demonstrate it, for example, with complementation. When we complemented automata on finite words, we just had to dualize the set of accepting states. If I do the same here, and I move to this automaton does not complement the previous automaton. It doesn't accept all the words with only finitely many ones, because now it accepts all the words with infinitely many zeros, and this is not equal to all the words that have infinitely many ones. For example, the word 0, 1, 0, 1, 0, 1 forever, right? It has both infinitely many zeros and infinitely many ones. So complementation, it's not clear how we can do it, and if we want an automaton for this language of words that have only finitely many ones, we will need non-determinism. Here is a non-deterministic automaton for this language. Indeed, it accepts exactly all words that have only finitely many ones, because now the automaton guesses when the tail of zeros starts, right? Because what is only finitely many ones? It means that I have some finite prefix with both zeros and 1, and then a tail of only zeros. The automaton guesses that it is now in this tail. And in fact, there is no deterministic automaton for this. So this is like a proof that indeed the setting of infinite words is more complicated. Not all non-deterministic automata can be determinized. So I'm writing this mainly in order to introduce three-letter acronyms that we are going to use. So let's first see the acronyms and then see what the so says. So in these acronyms, the first letter will tell us what the branching mode is, whether it is non-deterministic or deterministic. The second letter, the acceptance condition. I mentioned Buki, and we saw finite automata. There are more acceptance conditions, Kobuki, Rabin, parity. And an automaton can also run on trees, not only on words. So these three-letter acronyms will help us to refer to classes of automata. And what we saw so far is that NFW are equal in their expressive power to DFW. We can determinize, but NBWs are stronger than DBWs. Why did Buki introduce Buki automata? Because he and many other people really wanted to solve the decidability of second-order logic with one successor, and he managed to make a reduction to take a formula, S1S formula, and translate it to a Buki automaton for the models. And this is helpful because now, in order to check whether the formula is satisfiable, I reduce it to the combinatorial problem of checking whether the automaton is non-empty. And Buki didn't care much about complexity. It was in the 60s, people didn't implement automata or want to do something with them. They just were curious about borders of decidability. But then in the 80s, formal methods arrived, and then automata started to be useful in practice, mainly in formal verification, in reasoning about ongoing behaviors of reactive systems. So one good thing about it is that the motivation part is very easy. We don't want bugs, and automata can be helpful, as we will see. And when we use automata, we are starting to care about things like complexity and succinctness and things like that. How do we use automata in formal verification? So first, what do we do in formal verification? One basic problem is model checking. We get as input a system and the desired specification for it. We press a button, and we get an answer to the question, does the system satisfy the specification? And if the answer is no, we are getting a counterexample. And in the automata theoretic approach, it is based on our ability to translate specifications. Here it's in linear temporal logic, a logic that describes computation, to an automaton. It is like the translation of Buki, but if we start with temporal logic, things are much simpler. There is only exponential translation. I'm saying only because for Buki it was non-elementary. For all the models of the formula, and the system M satisfies the specification phi if the language of M, the set of all computations, and this is something we can define with an automaton, is contained in the language of the specification, and we can reduce it to a question about automata, whether the language of the system and an automaton for the bad computation, so here there is not phi, whether it is empty. We are checking that there is no computation that is both a computation of the system and the computation that violates the specification. And this is something that we do, and this is really used in practice. This is how people in the industry check specifications in LTL. Another application is synthesis. We have a specification, we press a button, and we get, wow, a system that satisfies the specification. So no need for verification. The system is guaranteed to be correct. Very useful because the specification can be abstract. It doesn't have to specify the implementation details. We just specify the required behavior. And then what this process does, a good thing to think about it is, like, this is where automatically we add semaphores and queues and all the implementation details that are required in order for the specification to be satisfied. So the slogan for synthesis is that it enables the designer to focus on what the system should do rather than on how to do it. This is like the thing that we want to automate. How do we solve synthesis? It's important whether we talk about closed or open systems. A closed system does not interact with an environment. It just generates an output. So it may seem boring, but this is an output that is an ongoing, an infinite computation. So if you think about a counter or a light show, yes, there are interesting things to specify also for a closed system. And the correct closed system is one whose single computation satisfies the specification. And the specification is over a set O of output signals. More interesting are open systems, and open systems think about buttons. They interact with the environment, so the form of interaction is that first we have to say which signals are input and which are output. An input arrives, the system generates an output, and the output, of course, may depend on the input, so we will say that that O1, that's the assignment, the first assignment to the output signals, depend on I0, which is the first assignment to the input signals. So O1 is a function of I0, then another input arrives, and now the next output may depend on all the history of the input so far, and so on and so forth, and we get an infinite computation. And the correct open system satisfies the specification, and the specification is now over both the inputs and output signals in all environments. So no matter which inputs we are going to get on the right, the induced computation has to be correct. And how do we solve synthesis with automata? So for closed systems, where we have a specification just over output signals, what we really need to generate is just a single computation that satisfies the specification. So once we know how to generate an automaton, and the alphabet of the automaton is assignments to the output signals, then a closed system that satisfies the specification is just a witness to the non-emptiness of this automaton, and non-emptiness is easy. We are talking now about bookie automata. Remember that a run is accepting if it visits the accepting states infinitely often. So you have to find such a lasso, and U goes from the initial state to some accepting state, V loops, and the UV omega is a computation that is accepted by the automaton, and therefore it satisfies the specification. And now things are starting to getting more involved. Note that for this automaton, we don't care whether it is deterministic or non-deterministic, right? When we check non-emptiness, we just have to find the path from the initial state to an accepting state, and the path back, and it's not important whether the automaton is deterministic or non-deterministic. It's okay. And the same thing happened when we did model checking and checked the non-emptiness of this product. We could work with non-deterministic automata. When we solve synthesis for open systems, and now the specification is over inputs and outputs, and we want an open system, one that interacts with an environment and satisfies the specification in all environments. Remember this. So what do we do? So first we view this setting as a game. And whenever we design an open system, we really design winning strategies in a game against the environment. The system wants the generated computation to be correct, to satisfy the specification, and the nasty environments wants to provide inputs that would cause the system to generate a bug. If we have a correct system, we have a winning strategy. We will always satisfy a correct computation. Formally, it looks like that. A strategy F, and first, what is a strategy? What's the type? A strategy is something that takes sequences of assignments to input. That's the history of the input so far, and generates the next assignment to the output signals. So a strategy F realizes a specification phi, and the specification is over both inputs and outputs. If for every input sequence that we get, Wi, the output sequence that is generated by the system is such that, and here you have the thing that I hope you expect it, what you expect it to be. Yes, so this is the computation that is obtained by combining the sequence of inputs with the sequence of outputs. It has to satisfy the specification. How do we solve synthesis? We need to find such a strategy. So if, for example, yes, just to make sure we understand the definition, so here is a short example. So suppose the specification says that if you don't know LTL, here we use G and X. G is always, and next is X is next. So this specification says that the computation is such that it is always the case that if I have two successive positive I, if I and next I, this happens if and only if next O and next O. So I have to generate two successive true assignments for the input signal O, if and only if there are two successive true assignments to the input signal O. So suppose the environment gives me in the first cycle true, I can generate F. If I get F, I can generate F, and so far so good because we still don't have an evaluation for the right-hand side. But for example, here there is just a single O that I can put here, and the specification would not be violated. Which one is it? I am looking at these two assignments, T and F. So I and next I is false. So O here and the next O should also be false. In fact, I can do both, but I'm doing false. But never mind the exact details of the example. This is how the interaction goes, and this is what I need to automate. Something that will tell me what to output, such that the specification would be satisfied, and first to decide whether this is possible, right? Sometimes it is not possible to win in the game. In this example, it is. So a system wins in this game if the generated computation satisfies the specification. Otherwise, the environment wins, and we want a winning strategy for the system. How do we solve it with automata? So now we are going to translate the specification. Let's start with a deterministic automaton. We start and translate it to a DBW, deterministic bookie word automaton, which also means that I cannot handle all specifications, but let's leave it for now. We call it dphi for the models. This is our automaton. And now we play a game, and we denote this game as the game played on the automaton dphi with input signals in I and output signals in O, because it's important which signals are input and which are output. And the game starts in a position that is the initial state of the automaton. Then the environment, whenever we are in some position Q, in particular in Q0 when the game starts, the environment chooses some assignment I to the input signals, and with the system, we choose an assignment O to the output signals. So we respond with the output signals, and then the game proceeds to the next position, and the next position is the delta of Q, and this is a letter, right? Because we work with an alphabet of assignments to inputs and outputs. So we move to the next state of the automaton, the state that corresponds to what happens when the automaton is in state Q and it reads the letter I union O. So the games move to the next position and continues like that, and the system wins if and only if the sequence of positions satisfies the specification. And it makes a lot of sense, right? Because it means that it was able to respond with assignment to the output signal such that the run is accepting. If we go back to formality, but if you lost me here, don't worry about it. Yes, it just means that the run of the automaton on the generated sequence is indeed accepting. And now let's try to do it with a non-deterministic automaton. And now, what's the difference? So first we have to write N, and we will call the automaton A and not D. But in the game itself, when the system moves, it's not sufficient, it's not enough for the system to choose an assignment to the output signal. It also has to generate the accepting run. So the system responds with both an output and the state Q prime in delta of Q and I and O. It resolves the non-determinism. It also says, okay, this is the letter. I complete the letter. The input part of the letter is given by the environment. I complete the letter by an output, and I'm giving you the accepting run. On this, the game moves to the new position, Q prime, and the system wins if the sequence of positions satisfies the specification. And it looks good because the system also provides the accepting run of the automaton. And it is also sound in the sense that if there is a winning strategy for the system, there is also a system that satisfies the specification. The system will do exactly what the winning strategy tells it to. But we are going to see that it is wrong on the other direction. So why is it wrong? Remember that the winning strategy for the system has to do two things, to give a correct assignment to the output signals and accepting runs of the non-deterministic automaton on the computations that we generate. Now suppose, for example, that we have this situation, that in the automaton we have a state Q8, delta of Q8 with some letter A has several possibilities, Q1, Q3, Q4, and we have a word, so this is where we stand in the automaton. We are in state Q8, and now we read the letter A. This circle here, I read the letter A, so I have to choose a state in delta of Q8 and A to move here. And suppose that W1 needs an accepting run. Sorry, the A is here. The A is here. Q8 with A, I need to move to Q3 in order to accept the word Q1. So the word Q1 is in the language, and there is an accepting run of it. I proceed from Q8 to Q3. But I also have another word, Q2, which also has an A there. And in order to accept Q2, the accepting run has to move from Q8 to Q4. In this case, there is no winning strategy for the environment, for the system, because the system still doesn't know the future. It doesn't know whether from here it will have to accept W1 or W2. So when it is in state Q8 and it gets an A, it doesn't know whether to proceed to Q1 or to Q4. Or I don't remember, it was Q3, right? Because it doesn't know the future. And this is why we have to talk about soundness and completeness of our game. Soundness means that if the system wins in the game, then the specification is realizable. And the realizing system is induced from the winning strategy. We have a solution to the synthesis problem. And the soundness is okay. The game is sound for both non-deterministic and deterministic automata. But we also want to talk about completeness. Completeness means that if the specification is realizable, then the system wins in the game. And for completeness, we have a problem. The game is complete only for deterministic automata. It is not complete for non-deterministic automata for the reason we saw, because the future of the computation is unknown to the system. This is bad. This is bad because we don't like deterministic automata, especially in the context of automata on finite words. Determinization is complex, and indeed, the synthesis problem is doubly exponential complete. And we want to know whether we can avoid this determinization. And I'm going to show you two approaches to avoid this determinization. The first approach is to generate something that is almost complete. So we know that we cannot always succeed because the problem is doubly exponential hard, but the approach will be almost complete. Sometimes we will get a no, even though the specification is realizable. And the second approach is to work with automata that are almost deterministic. So it's two different approaches. Let's start with the first one, almost complete. So what's the idea? The idea is that games are determined. Whenever we play a game, in particular our synthesis game, one of the players is guaranteed to win. This is a result from game theory. It's a Borel game. There is a winning strategy for one of the players. So either phi, our specification, is realizable by the system, or the negation is realizable by the environment. So what does it mean not phi is realizable by the environment? That if we play the dual game, where the the system provides inputs, outputs, and the environment responds with inputs, then the environment wins. So this is the idea. The first item in the idea: games are determined. Then the game that we play is sound. If the system wins, then phi is realizable, and it is sound also for the dual game. Also, the game played on the negation of the specification, the automaton for not phi is also sound. If the environment wins in that game, then not phi is realizable by the environment. So what's the algorithm? We first check whether the system wins in the game with the non-deterministic automaton. If so, if we get a positive answer, we are happy. Yeah? Even though it is not complete, it is sound. If the system has a winning strategy, and often it has, we return its winning strategy. Then we check whether the environment wins in the dual game, whether the environment can realize the dual specification, the negation. If so, we know that because of the determinacy of games, we know that this is not because of determinacy, this is because the other player wins, then we can declare that the specification is not realizable because the environment has a winning strategy. Only if these two things don't succeed, we have further heuristics. What are the further heuristics? They have to do with universal satisfiability. What is universal satisfiability? A specification is I/O universal satisfiable, so it's a specification over inputs and outputs. So the thing that says here is that for every input sequence, I can generate an output sequence such that the combinations satisfy the specification. What's the difference between this and what we defined for realizability? That here the output sequence is independent. Yeah, I don't need a strategy that generates it. I just have that some output sequence needs to exist. So it's not exactly like realizable. If a specification is realizable, then I know that it is universally satisfiable because I can use the strategy in order to generate this output of sequences. But if a formula is universally satisfiable, it doesn't mean that it is realizable, and I hope you see some connection to the fact of to the existence of non-determinism and the challenge of the need to associate the same outputs to computations with the same prefix of inputs. As a specific example, think about a specification. It is always the case that the next input will be positive if and only if the current output is positive. This is something that is universally satisfiable. Once I am giving an infinite look about the future. When I see the sequence of inputs, I can plug in outputs in a way that will satisfy the specification. But I cannot do it in an online manner, which is the point in synthesis. And checking whether a formula is universally satisfiable, it is easier than synthesis, and it is not very easy. It is X-space, but we don't need a deterministic automata for that. So now what would be our algorithm? It will start as the previous algorithm. We check whether the system wins in the positive game. Then we check if so, we are happy, we have a transducer. We check whether the environment wins in the dual game. If yes, we are also happy because we have a solution that we may not be very happy with because it means that the system cannot be synthesized, but we have a solution. And if not, we continue and we check whether it is universally satisfiable. Now what will happen? If the specification is not universally satisfiable, then we are done. Because we know that if it is not universally satisfiable, we have no chance to generate a transducer for it. And we also check, if we need, whether the specification, the dual specification is, here we have OI universally satisfiable, which is what you expect it to be, that for every sequence of output signals, I can generate a sequence of input signals such that together they will be satisfiable. And if the specification is not universally satisfiable, what do we know? We know that the environment cannot realize the negation, and therefore from determinacy of games, we can realize the specification. So we are done and we are happy. We know that the specification is realizable, and we even have a system that generates it. Why? Because if it is not universally satisfiable, we know that there is some sequence of outputs such that for all inputs, the specification is satisfiable. If you lost me, it's just the definition, and our system can simply ignore the inputs and generate always this sequence of outputs. If not, then we have further heuristics, and these further heuristics are based on doing a partial subset construction on the game, and I'm not going to get into the details because what we really want to talk about, and if you lost me, then a new lecture starts now about the second approach, which is how to use automata that are almost deterministic. So let's start, and these are the history deterministic automata, but this first approach, by the way, it was implemented and it works many times. We don't have to get to this stage of refining the game by some local subset constructions. So what are automata that are almost deterministic? Let's look at this automaton and now view it as an automaton on finite words. What's the language? So you can see that there is 1 point of non-determinism. With 0 here, I can either stay in Q0 or move to Q1. And you can also see that I can loop in Q0 and then guess that I'm going to read 0, 1, 0, and then move to an accepting sync. So I'm clearly accepting all words that contain the sequence 0, 1, 0. And in fact, I'm not going to accept more than that, because if I'm using this transition, it is still the case that there is a sequence of 0, 1, 0. And if I'm taking the one transition back, then it's kind of a reset. So the language of this automaton are all words that contain 0, 1, 0. And in fact, it is true also for infinite words, because the accepting loop doesn't care whether it's a finite or infinite word. The interesting thing about this automaton is that it is indeed non-deterministic. But if I remove this 0 here, and they make it deterministic, because that was the only non-determinism, it still accepts the same language. And we are going to say that such automata are determinizable by pruning. I can remove some transitions that cause the automaton to be non-deterministic, and get an equivalent automaton. And you can see that this is really the case in this automaton. I still accept all words that contain 0, 1, 0, because this is the, I'm not going to show you, but you can see that if whenever there is a 0, I'm hoping to see 1, 0, and I will stay here. If I read 1, 0, I accept. If something bad happens, then I get back to the initial state. So this automaton is determinizable by pruning. What happens if we play our game with such an automaton that is DBP, determinizable by pruning? Is it sound and complete? So sound for sure, yes, because we know that even non-deterministic automata are sound. And it is also complete. It is also complete because the system player can ignore all the transitions that are, they can play as if it was a deterministic automaton, can follow the transition that works for all futures. If we look at the thing that bothers us earlier, then you can see that when I am in Q8 and I read the letter and I know that I could prune all the non-deterministic choice other than Q3, then I will simply follow in my synthesis game this strategy and go to Q3. So I resolved non-determinism in a way that works for all the futures. And in a DBP automaton, it's the same choice for all the visits in a given state. What do I mean by that? Something here happened. Okay, let's do this definition first. So I will say this slowly. In a DBP automaton, are you? Yes. Right, and this will be the definition. But in a DBP, if someone tells you, yes, this automaton is DBP, there is a way. It's even it depends on the acceptance type of the automaton. For finite words, it's polynomial. For infinite words, it's NP-complete, but you can find the determinization, and then you can follow it.
This is possible, then, sorry. If I know that this is possible, then I can find a way to do it for these automata?
Yes, and then your strategy will follow this choice as if you start with a deterministic automaton.
And if I don't know that it is prunable, can I still try and...
so we will see that, yes, it's an excellent question, and yes.
Thank
you. But the important thing in a DBP automaton is that whenever I am in our example, whenever I am in Q8 and I read an A, I will go to the same choice for all the futures. And in history, deterministic automata, introduced by Hensinger and Peterman in 2006, things are more flexible. They resolve non-determinism in a way that only depends on the past. How? So formally, when is an automaton history deterministic? If I have a strategy that, given the prefix of the word so far, tells me how to continue. And it doesn't have to be the same whenever I'm reaching the same state. So there is a strategy F that maps finite words to state. This strategy maps the empty word to some initial state. Now we are in a non-deterministic automaton, so there may be several initial states. So the strategy first tells me with which initial state to start. And then if I am in I read so far W and a new letter sigma arrived, then the function F, this strategy that resolves the non-determinism, has to be correct in the sense that the state that I'm getting is a possible successor. It is in delta of F of W and sigma, and it is guaranteed that if a word is in the language, then the strategy works. F of W is accepting, and F of W is just the sequence of states that I'm getting when I read W. and this is the example I thought was in the previous slide. Yeah, so if delta of Q8 and A, it has 3 choices, and the strategy of the G of G automaton tells me that after reading W1, I am in Q8, and after reading W1 with A, I have to move to Q3, then I know that in all the futures that starts with W1A, they will be accepted by going to Q3. But there may be another word, W2, and this word W2 also reaches the state Q8, and when I read A from Q2, the strategy tells me to proceed to Q1 rather than to Q3. Yeah, so it's not, it doesn't have to be determinizable by pruning in the sense that I cannot erase all the transitions from Q8 and stay with a single transition. But whenever I am in Q8, based on my past, based on whether I got to this state Q8 with W1 or W2, I know how to continue. So let's see some examples. So the first examples are automata that are determinizable by pruning, and there, just to formalize the fact that every determinizable by pruning automaton is history deterministic, the function W, the strategy of the HD automaton after reading a word W will just take me to whatever the transition function after the pruning takes W. Is there an automaton that is history deterministic and not determinizable by pruning? So for finite words, we know that the answer is no. For finite words, we know that an automaton is history deterministic if and only if I can determinize it by pruning. For infinite words, the answer is yes. There are HD automata. There is a non-deterministic Bookie word automaton A such that it is history deterministic. I can resolve the non-determinism based on the past, but every pruning of A to a deterministic automaton reduces its language. I am going to miss some words. Can we get more expressive power? Because we saw that deterministic automata, Bookie automata are less expressive. So here the answer is no. And we can determinize HD automata. It was shown already in the setting of 3 automata, but then a determinization construction that is presented on history deterministic automata. And the idea is quite simple. I can do the simple subset construction. The same thing that works for automata on finite words would work for HD automata. Formally, I have a set of states, so S is now a set of states, like in the usual subset construction. And whenever I am in a set S and I read the letter sigma, if this set does not intersect, the new set does not intersect alpha, I move to all of it. But if it intersects alpha, I move only to states in alpha, and this transition is considered good. So we are working here for simplicity with automata whose acceptance condition is on the transitions. I'm not going to get into the details. The result we wanted to say is that HD automata need not be determinizable by pruning, but still they can be determinizable. Can they be smaller? Can I define automata that are history deterministic and are smaller than deterministic ones? What do you think? For finite words, no, because for finite words I know that if I am HD, then I can determinize myself by pruning transitions, so I am not smaller. For infinite words, it is open. It depends. It depends. For Ko-Bookie automata, we know that there is an exponential gap, and we are going to see this gap. It's an amazing result. So I'm history deterministic, and still I am exponentially smaller. For Bookie automata, in the same paper, Danny and Mikau, I'm not able to pronounce the last names, they showed a quadratic determinization for non-deterministic, for history deterministic Buki automata, but there is no matching lower bound. And in fact, here in ATVA, we have an alternative construction, a quadratic determinization for the Buki case, but there is no lower bound. But let's see how they are exponentially more succinct. The result by Danny and Mikau, how still I am history deterministic and I can save exponentially more states. So we are talking about Kobuki automata, so NCW, non-deterministic Kobuki word automata. A run is accepting if it visits states in alpha only finitely often. Yeah, so it's the dual of Buki. So what are we going to see? We are going to see a family of languages, L1, L2, L3, and so on, such that for every n, the language Ln can be recognized by a history deterministic Kobuki automaton with n states, but a minimal deterministic for the language needs exponentially many states. So somehow, knowing the past enables the automaton to resolve the non-determinism in a way that guarantees the acceptance of all words. In particular, the automaton can be used for synthesis in the synthesis games, and I'm still exponentially more succinct than a deterministic automaton. So here is the language Ln. So here is an example where n is 5. So we are going to view words as an infinite grid with n lines. Yeah, we are going to number them 0, 1 up to n minus 1, and each word is going to describe graphs on this grid. How? We are going to have 4 letters. The letter I, and whenever we read the letter I, we are extending the grid with this structure. Yeah, I is like identity, nothing happens. Yeah, you can think about each letter as a permutation, but we like to see it in a visual way. But I is just the identity permutation. If I was in floor 2, I say in floor 2, in line 2. Then we have the letter Z. I tried, so I'm showing you something that is a bit different from the original idea in the other paper, but it's very, very similar. So Z does this permutation. Every floor goes one floor up, and it's cyclic. Then the letter X just switches floors 0 and 1. And the interesting letter H is for whole. It makes a whole in line 0. Okay, so if I am getting the word here on the top, this is the graph that is induced. And really think about it as a graph. Yeah, the floor 4 starts like that. And you can see that sometimes lines are broken. Yes, if a line reaches floor 0 and then H is read, then the line is broken. So what's the language Ln? The alphabet is these 4 letters, and also note that we have 4 letters and 4 is independent of n, right? So for every n, we will have the same 4 letters. And Ln is the set of words W such that the graph induced by W contains an infinite line. Not all graphs are going to contain an infinite line, right? Because it may be that I'm reading some pattern that will cause a line to break and then will cause another line in another floor to break, to go up to 0 and break. So the good words are words in which eventually here there is a chance that floor 1, for example, will continue. Yes, if I repeat this pattern infinitely often, then the blue line, it goes from 1 back to 1 again and will repeat again and again. So the word we saw, if we take it in an omega, it will be accepted. Let's first find a deterministic automaton for it. And the deterministic automaton is going to maintain in each state the set of lines of floors that survive, that are still okay since the previous breakpoint. This automaton is going to have a breakpoint. We start in the beginning. The beginning is a breakpoint, and we maintain the set of lines that still have a chance of containing a line that will continue forever. So S is a subset. This is the exponential automaton, the deterministic exponential automaton, a subset of the numbers from 1 to n minus 1. And if I'm starting with some set, and for example, I'm reading I does nothing, so I stay in S. If I'm reading age, I will move to the set of S without 0. It's on. No, let's wait. It's getting closer. Okay. So the specific example for L4, so we start with all lines are candidates of hosting an infinite line. Then if I read I am staying because all lines are still candidates, are still in a line that didn't break, and the same if I read Z and I read X, because 0 and 1 are switched, it's okay. A shift, still this is the set of lines. But if I read an age, I move to a state that says now only floors 1, 2, and 3 host lines that have a chance to continue forever. Now if I read I and age, I'm staying here, but if I read X, what will happen? X, you can see it here that X switches 0 and 1. So if I read an X, I will move to a state in which instead of the 1, I have 0, because now this is the set of floors that are, we can call them alive. I always makes me loop. If I read Z here, then there is a shift. So the 1 becomes 2, the 2 becomes 3, and the 3 becomes 0. Yeah, so it goes like that. If I read age, I have to remove the 0 because line 0 is broken, and so on. The interesting thing is what happens when only 0 survived. So this is the only floor that still has a chance to be continued to an infinite line, but I read an age. What will I do? I will make a Kobuki transition, a transition I want to traverse only finitely often. We are working with Automata on acceptance on the transitions just to save a state. So I'm moving, this is the breakpoint I was referring to. I'm starting from the beginning, but I do it with such a Kobuki transitions. And if the run of this deterministic automaton is accepting, if it visits this line only finitely often, then it means that eventually I reached this state, and from this state I didn't need to take this transition. So there is some set of lines that survives, and there is an infinite line. So everything is well, except that we needed exponentially many states. Questions or something about the language?
Thank you. C and X here seems doing very similar thing. Why do you need both?
Because if I only had X, I could only switch the 0 and 1s, right? Line 2 and line 3 would never make it up, right?
But can we have only C?
So now, okay, so I didn't answer. And now if I only had Z, I mean, the real answer would be we have here permutations, right? And the question is with which set of permutations I can generate, with which local permutations I can reach all permutations. And I need both of them in order to reach all permutations. So that's the... More questions?
Yeah, so I wondering if the proof or anything is going to something about permutation group.
The formal proof of why we really need these many states has to do with it.
Yeah, and then also the
I is not required. So the I is not required.
And then also, is there something like if it's prime number or something will make it?
So that's for the offline discussion.
Okay.
Yeah,
Okay.
I just want to make sure you understand what's going on. Yeah. So this is the language, and it needs exponentially many states. And now we are going to see a small non-deterministic automaton for this. And the small non-deterministic automaton can guess a line that survives. So it starts with the 4, we are in an example with 4 floors. We are starting, for example, in floor 1. And if we read I or H, we see what happens to line 1 with, it stays in floor 1, both in I and in J. And if I read the Z, the 1 becomes 2, right? Because 1 goes down to 2. If I read an X, I move to 0. And you can complete it if I am in line 2 and I read H, X, or I, it does nothing to me. If I read the Z, I become 3, and so on. The interesting thing is what happens when we read H. Okay, so I completed this, and if you follow line 0 and read H, what to do? That's the interesting thing, and that's where the guessing is. We are going to take an alpha transition, a bed transition, to all new, to all the possibilities. Yeah, whenever I'm in a run and I'm in floor 0 and an edge arrives, I am guessing whether the infinite line that I hope to find will start from 0, from 1, or 2 and 3, which is why I'm adding these edge transitions to all the states. And it works, it's easy to see that it is correct. The complicated thing is to see that this is a history deterministic automaton, which is very amazing. I allow myself to say it's amazing because it's not my result, yes. How, when we are in state 0 and we read an age, we know how to guess to which floor to jump just based on the facts. So let's see what's the strategy, what's the HD strategy. So suppose we start, our run starts with floor 4, and the run continues, and we got here and we read an age. To which floor continue? Based on the past. So the strategy tells us, the HD strategy is to always move to a line with the longest history. Here, all the other lines have the same history. They all started in the beginning, so it's not very important. And the idea would be that if an infinite line exists, then it would eventually become a line with the longest history. So suppose, for example, we jumped to line 3, and the run continues, and again, we got to line 0 and read an age, and we need to make a non-deterministic choice. Where to go? We are not going to go to floor 1. We are not going to go to floor 1 because floor 1 has a short history. There are lines with the longest history. So we are not going to jump here because these two lines have, these other 3 lines have a better chance of being a start of an infinite line. So suppose we jump to 3. Again, where to go? We may go to 1 because 1 has the longest history. And again, the idea is that if an infinite line exists, it would eventually become a line with the longest history. So this is how we were able to use the past to direct us how to resolve non-determinism, and it saved us exponentially many states. So exponential saving in Ko-Buki automata, and again in Buki it's open. We have a quadratic upper bound, it's only quadratic. Yes, we know, and that's also very interesting, the fact that for Kobuki there is an exponential blow-up, but for Buki there may be some saving, but not more than quadratic. Many more open problems about history deterministic automata, minimization of history deterministic automata. We know, yes?
Yeah, I don't know if, maybe it's a stupid question, but if I start in 4, right, the red thing, then, so what is my memory? I think that's my question. So how do I know how the other runs that started?
It's an interesting question. Your memory is exponential. Your memory is exponential because once you have a memory, you have a deterministic automaton. But in order to solve the synthesis game, you don't need this memory. I mean, you can play the synthesis game on the linear automaton. I'm very happy for this question.
Okay, thank you.
The automaton is small. The memory that resolves the non-determinism has to be exponential, but I can still play the synthesis game on the small automaton. The memory is a deterministic automaton.
Okay, thank you.
Soon we will get to the questions at the end. So that's because these are counted on my time. The questions on the end are not. Yeah. So many more problems. We mentioned minimization. We know that minimization, and I'm saying we know, but if you don't know it, it's a very nice result. That minimization for Buki and Kobuki automata is NP complete, unlike automata on finite words. And it's not clear what happens in history deterministic automata. We know, for example, that it is polynomial for Kobuki automata with transition-based acceptance. There are input-output aware HD automata. Automata that are HD in the input component of the alphabet and non-deterministic in the output component. And in fact, when we play the synthesis game, we can use also such automata, and they may be even more succinct than general HD automata. There are richer models that were studied, alternating automata, push-down, weighted history deterministic automata. It's just another form of non-determinism between deterministic and non-deterministic. Our automata, they were previously called good for games automata. We changed the name for history deterministic because in the richer models, they need not be good for game, but they are also good for other things automata. Other applications that traditionally use deterministic automata, but now we know that they can work with some form of non-determinism, especially there are automata that are good for probabilistic reasoning, good for MDP automata, and they are also useful. There are additional models between the non-determinism and deterministic models. So we saw determinizable by pruning, which are automata that are non-deterministic but have some form of determinism. There are semantically deterministic automata that have non-determinism, but the non-deterministic choices lead to states with the same language. Again, in finite words, it's like a deterministic automaton, but in automata on infinite words, it is not. So to sum up, for some problems, in particular synthesis of closed systems, we can work with non-deterministic automata, but for some, in particular synthesis of open systems, we cannot. We have to use deterministic automata, but we can avoid determinization. One possibility is to approximate the response, use determinacy of games, and the fact that the synthesis game has only a one-sided error in working with non-deterministic automata. And the other is to approximate the determinism to use HD automata, fascinating and useful with many interesting open problems. Go ahead. Thank you.
So thank you, Orna. We have time for a couple of questions.
Thank you. So one issue that I see with the specification formalism is there is no notion of causality when you specify inputs and outputs. So you can specify whatever you want, and the outputs can actually anticipate inputs that come out into the future, right? But in areas like controls, control theory or systems theory, we always insist on defining things in a causal manner. Like you can't specify future like outputs now that depend on the future inputs. Have people looked at like taming the specification language?
Yes, and it's an excellent question. There are specification formalisms like GR1. GR1 synthesis is simple, and one of the reasons it is simple, or at least simpler, is that we have this causality. The specifications are of the form infinitely often assumptions implies guarantee. The assumptions can refer also to inputs, but really there are history variables and things like that. So yes.
I have a different but similar flavored question that also comes from control. So there often, I mean, in continuous systems, you try to predict the future evolution of your continuous variables over a bounded horizon, and then you already react to that. So transferring this here, I was wondering if you would gain something, if you would know like a shortly bounded future, and in addition to the past, like have people looked at this?
So there is work on synthesis with a bounded look ahead. So that's the way we formalize it. It actually, it does, I'm not familiar with works. I think they do not exist on the combination of look ahead and history determinism, but just synthesis with a look ahead, it exists, and it is indeed.
And what is your intuition? Like if one would add that, would you gain something? Like
yes, but it will be orthogonal. I mean, the same way it helped without history non-determinism, it will be combined in an expected way. Still helpful, but...
Okay, so you don't think combining them would gain something in addition to the...
No, it would combine, but I'm not sure it will be theoretically interesting. I mean, okay. You can think of the example we show, right? If instead of an edge that cuts the line now, you will get a letter that will cut the lines in some K positions, then the K look ahead would help you. Yeah, so things are expected, but it's still useful. Yes.
Okay, thank you.
Hiya, thanks. I guess it's a question probably in a similar vein to the last two questions, but with the memory slide you had, it seemed a surprise to me that when the line was cut, when you made the decision about checking the length, that you chose only a short length, because surely you could be considering lines which have been cut.
So no, we wanted to go to the line that has the longest history so far.
Yeah. Well, maybe it was just the diagram then, but it seemed like you considered the history from somewhere in the middle rather than from the very beginning.
Because I'm looking at the present and the longest line that survived, the longest possibility to go back.
Okay, sure. Okay, I think that probably answers my question then, because it seemed like maybe you could consider
in the figure I showed what not to do. Perhaps that's what
confused me, sure.
Yeah, so that was not to one.
Yeah, because I guess in the next one you then had the purple line which started where the question mark is currently.
But we know that eventually, if there is an infinite line, then it will become a one with the longest past.
Yeah,
that's
great.
how we use the past.
Cool. Thanks.
Okay, thank you.
Okay, so
Is there one? Okay.
there is also this line of work by limiting the accepting condition to like having only exactly let's say k number of visits to the accepting states, and in that case, the determinization can be made very easy, and some people are using this for the synthesis of open system. Have you looked into like the relations between these two kind of like formulations? And,
So what you describe seems to me like a special case of safety and co-safety. languages. And for them, we know that all history deterministic automata are determinizable by pruning.
Okay, so let's before we let's leave for a coffee break. Let's thank Orna again. But before we leave, Ichiro has an announcement.